Okay, we are discussing about the metal casting operation. Today also we are continuing with this topic. Today we are going to discuss about the other furnaces type and also the different type of casting processes. Okay, let's move to the theory of this subject. Okay, last class we discussed about the cupola operations, then cupola furnace. Then today we are going to discuss, we are studying with the electric arc furnace. Okay, electric arc furnace. Okay, electric arc furnace. The electric arc furnace use the electricity to produce the heat. Okay, electricity to produce the heat. Okay, then I will draw the electric arc furnace first. This is the structure of the electric arc furnace, having the dome shape structure. The upper part can open. Okay, the inner in the dome shape. The one end is open to take out the motor metal. Okay, then this is the electrodes. There's a 3 carbon electrodes. They normally use the three electrodes. 2 electrode, single electrode arc furnace are also there. Three electrodes. Okay, these are carbon electrodes. Carbon electrodes. Then this is the charge material. In here the material is this top half can open. Then the charge materials are charges to this cabin. So then this is the, let's take, this is the motor metal. Okay, and this is the motor metal. Motor metal. Then this is the slag layer. Slag, the impurities layer. It is floating on the motor metal. Then there's a hole to take out the slag also, called the tag squirt. Okay, tag squirt, slag squirt. Slag squirt. Here this is called the tapping squirt, where the motor metal is taken out from this tapping squirt. Then the motor metal is taken to a ladle. Okay, it's kind of a ladle. Okay, this is called a ladle. Then inner is inner having its inner having the refractory layer. This inner having refractory layer. Inner refractory layer. And the steel housing. Okay, this is steel housing. Then inner having the refractory layer. steel housing, the steel housing. Then it also mounted on the this kind of that means by tilting this electric arc furnace, the motor metal can take out. There's a tilting mechanism. The hydraulic jack is used to tilt the furnace. This is the hydraulic jack. Okay. By operating this hydraulic jack, this entire electric arc furnace can tilt. Then motor metal can take out to the ladle from the tapping spool. Then how this is work? Then high power alternative current, the AC current also, and also the DC also can also use. High power current is supplied to the electrodes. High power current is supplied to the electrodes. Then what happens? The electric arc generate in between the electrodes. The electric arc, high temperature electric arc, normally this electric arc having the 3000 centigrade electric arc generate in between the electrode, and also electric charge generate in between the charge material and the electrode also. Okay. This temperature of the electric arc is around 3000 centigrade. Then the voltage ranges that is depend on the capacity of the electric arc furnace. Normally voltage ranges 400 volt to 900 volt. Then the current rating is varies, that also vary. Normally the greater than 44,000 ampere. Okay, this is normal voltage range and the current rating for this electric arc furnace. So that very high temperature electric arc generate in between the electrode and also the electrode and the charge material. Because of this high temperature electric arc, what happened? The charge material molten. Then after this molten, the slag spurt is used to remove the slag from the that means the slag is floating on this molten metal. Then easily this can separate using the slag spurt by opening the slag spurt. Okay. Then after removing this slag, by tilting the electric arc furnace, the molten metal can take out from the furnace. Then how we compare with this arc furnace with the other furnaces? What are the advantage and disadvantage in this melting with electric arc furnace? The main advantage of the electric arc furnace is the charge material composition we can closely control. Okay, charge material composition can closely control. Then another advantage is high melting rate. I will write that advantage also. Okay, then what are the advantages? High melting rate. Then and also the high pouring temperature. The high temperature can obtain using the electric arc furnace around that means pouring temperature around 1800 centigrade. We can obtain using the electric arc furnace when welding the steel. That is 1800 centigrade mean very good temperature for the pouring. Okay. Then another advantage is arc furnace then we can accurately control the alloy composition. What it means, actually this electric arc furnace used to melt the steel and also the steel alloys. Okay, especially the steel and steel alloys. That means by adding the alloying elements, the chromium, nickel, whatever the alloying component, the charge material composition, that means the this molten metal composition, okay, we can closely control. That means the carbon, if we can add the predefined amount of chromium, nickel and the carbon to this closed chamber, then and also the ferrous metal, the raw metals we can add, then the ferrous raw metal we can add as the form of pig iron or scrap iron. Then a required amount of alloy element, for example the chromium, nickel and carbon, we can add. Okay, we know the amount of kilogram we added charge to the ferrous, we charge to the chamber, and according to the weightage of the ferrous metal, we can add other required alloy component, alloy element to a predefined weightage. So that is the advantage in steel melting with the electric arc furnace. That means alloy composition we can closely control. Okay, alloy composition we can closely control. That is the main advantage with the electric arc furnace. Another advantage is there's no the fumes evolved, and also for compared to the cupola furnace, a lot of fumes are evolved. The dust, fumes, carbon blacks are evolved, carbon dust evolved in that process, but there's no that kind of fumes, carbon dust or whatever evolved. In cupola furnaces, we can produce only the cast iron. Okay, we can't control the carbon percentage in the ferrous metal in cupola operation, because earlier I explained in last class, the carbon percentage, there's no method to control the carbon percentage, because it's a molten metal directly contact with the carbon coil. So what happens, this carbon atom diffuse into the molten metal, then the carbon percentage increases to around the 4%. So then output is the cast iron in cupola operations. But in here we can closely control this composition. There's no direct contact with the burning fuel or coal. Then here, and also another advantage is high efficiency. Efficiency is very high. It uses the electricity, and the electricity directly converted to a heat energy with a greater efficiency. Okay, efficiency is very high compared to the fuel combustion type furnaces. Okay, then this transformer rating actually, for example, this is these electric arc furnaces are available with the few kilograms to the hundred of tons. Okay, lab type furnaces are available with a few kilograms of electric arc furnaces, lab type. Then in an industrial type, the hundred of tonnage electric arc furnaces are available. For example, if you take a 300 ton electric arc furnace, okay, it requires for the 300 ton capacity, to melt this 300 ton steel capacity, it requires around 132 megawatt hours. Okay, 132 megawatt hour energy is needed to melt the this charge material for the 300 ton electric arc furnace. Think how this is this much of energy. The 132 megawatt hour. Okay, what is our Victoria electricity power plant producing? How much of energy? It produces around 210 megawatt. No, think how much of energy is needed for this operation to make this kind of tonnage of molten metal. That means actually it can use this much of energy, and higher with the higher melting rate, it can produce quickly. That means can by consuming this much of energy, it can with a minimum time it can produce the molten metal. That is the main advantage. Another advantage, high melting rate. Okay. Then these are the advantages of the electric arc furnace. But this electric arc furnace are very expensive. Actually, it's contain a transformer, specific type transformer to produce the to generate the electric arc, to supply the electricity to generate the electric arc. The transformer that is also very expensive, and also these instruments are very expensive. Okay, these are very expensive. Then this is how the steel, this electric arc furnace used to melt especially the steel and steel alloys. Okay. Then next we are going to discuss induction type furnaces. Okay. Induction type furnaces. The next furnace, we discussed the cupola furnace and also we discussed electric arc furnace. The next type is induction type furnaces. The induction furnaces, called induction furnaces. Okay. The induction furnaces are used when high purity billet have to produce. Okay, high purity molten metal required. In that situation, the induction type furnaces are used. So what happens, I will explain the diagram. The induction type furnaces, this is just a illustrative diagram. It also having this kind of a charging container. Okay. Refractory container. Okay, refractory container. Then around this container, the copper coil is there. Hollow copper coil is passing around this container. Okay, hollow copper coil. Why is the hollow? Through the hollow, the water is passes for cooling. Okay. Yeah. Then if you look from the 3-dimensional view, I will just draw the 3-dimensional view also. This look like this. This look like this. This is the container. Okay. Around this, the copper coil is around this. Just illustrative diagram. Okay. Here it is only 2 windings are shown, but in real cases it having the 100 of windings around the container. Then this is the container. Then the charged materials are feeded to this chamber. Okay, let's take this is the charging material. Okay, charge material feeded to this chamber. Then high power alternative current. High power alternative current. High power AC current passes through this hollow copper coil. Hollow copper coil. So then what happens? Because AC current flows through this copper coil, then what happens? Because of this AC current, eddy current generate in the charged material. Eddy current generate inside the charged material. Okay, eddy current. You may heard this term called eddy current, no? In your A level, you may heard this word eddy current. Because of this electromagnetic force generated by this current carrying conductor, what happened? Inside this charged material, eddy current generated. This is the eddy current. I will show in this way. Eddy current are generated because of this fluctuating magnetic field. So what happened due to this eddy current flows in this charged material. Because of this eddy current flows through the charged material, it releases the energy. E is equal I squared R. Okay, E is equal I squared R. You know, when current passes through the conductor, it releases the heat energy, that is equal to I squared R. Okay, so then what happened when releasing the heat energy? Because of eddy current flow, the charged material get heated. The temperature increases gradually. Okay, temperature increases gradually. When increasing the temperature, what happen? The resistance also increases, so that the heat generation also increases. Okay, heat generation also increases. What happen? When it reaches to a melting point, the charged material get molten. Okay, this is how the induction furnace operate. This is how induction furnace produce molten metal which using the electricity. Okay, Okay, then these induction furnaces actually they available with the few grams to 100 of tons. Okay, 100 of tons induction furnaces are available. They used to melt various type of metals. Iron. Used to melt iron, steel, copper, aluminium like metals. To melt these kind of metals, induction type furnaces are used. Then actually the important thing is no the fumes or dust or any other impurities are involved in this process. The process is very clean. No the dust or fumes or involved. Then main advantage of this electric arc furnace is the high purity molten metal can obtain. High purity because there's no burning fuel contacting with the charged material, and also there's no this another important thing is this temperature gradually increases to a melting point. Okay, temperature gradually increases to a melting point. Let's take the room, starting from the room temperature. Let's take the steel 1500 centigrade. So gradually increases to the melting point, and further. Let's take the 1700 for the pouring temperature. So gradually increases, not the rapid increases like electric arc furnace. What happened in electric arc furnace? What happened in the previous case? It produced high temperature electric arc, very high temperature electric arc, around the 1300 centigrade electric arc is generated. What happened? The material in this region may oxidize because of this high temperature. The alloying element may degrade. And or change the chemical properties of the alloying element also because of this high temperature electric arc. But when using the induction furnaces, what happens? There's no that kind of high temperature concentration in this charging chamber. Okay? High temperature, there's no. That means the temperature gradually increases to a room temperature to a melting point and to the pouring temperature. So what happened? The high purity molten metal can obtain using these induction type furnaces, because alloying element composition not change because of the no high temperatures, and also the inner chamber composition can closely control. That means the predefined amount of required alloy element we can add according to the charge material. That means if we know the ferrous metal we are adding the kilogram, then we can add the required alloy element kilograms to this charging chamber. Nickel, chromium, carbon like element we can add predefined amount of alloy element we can add according to the weight we are charge ferrous metal we charge. And also it can use to melt the copper alloy and also the aluminium alloy also. In that when melting the copper and aluminium alloy also, the charging composition can closely control high purity product. That means the molten metal can obtain using the induction type furnaces. Especially the induction type furnaces are used to manufacture billet for the wire drawing. Especially the billet for the wire drawings are manufactured using the induction type furnaces, and also the cutting tools, specific type cutting tools are manufactured using the induction type furnaces, and also the electronic components, the material required for the electronic components are manufactured using the induction type furnaces, and also the specific metals required for specific projects. The specific projects mean space satellite, space project like situations. The materials are molten using the induction type furnaces. Especially for I explained this, the wire drawing. The wire drawing billets are manufactured using this induction type furnace, because in the wire drawing, this starting from this kind of billet, is converted to a thin wire, like this kind of thin wire, drawing through the set of die sets. To draw the set of die set, this material should be high purity and also the homogeneous, so that if there's an impurity or something, any change in the chemical or mechanical properties, what happens, wire may break, it cannot draw to a thin wire. Then this is the induction type furnaces. The induction heat is used to generate the molten metal. Then frequency is normal transformer. The why there's a hopper copper coil is used when transmitting the high power alternative current. This coil also get heated. To avoid the fusion of this copper coil, the water is passes through this hollow. Water is passes through this hollow. Okay, clear? It is clear. Okay. As a cooling for the coil. Then yeah. And this is the induction type furnaces. Okay, then next furnace type we are going to discuss is the crucible type furnaces. Crucible type furnaces. This crucible type furnaces actually used to melt the low melting temperature metals. We used to melt the low melting temperature metals. Okay, especially these crucible type furnaces are used to melt the low melting temperature metals like the lead, tin, nickel, like materials. Used to melt low melting temperature metals like zinc, tin, lead, aluminium, copper, like metals are molten using this crucible type furnaces. The the heat is generated using the combustion of fuel. They normally use the furnace oil, and also the kerosene and diesel furnaces are also used. Then the three types of furnaces are there. First one, the lift out type. Lift out type. Lift out type. Stationary pot type. Then the third type is tilting pot type. Okay, tilting pot type. The three types of furnaces are there. So then what happened, I will explain this lift out type first type. Then this is the flame. The crucible placed inside this kind of closed environment, and this is the crucible. Okay, crucible. After molten, this can lift out. Okay, this is the crucible. Okay. Crucible. After molten, that this crucible can take out. Then another type, the stationary pot type. This is the furnace flame. This is the flame generated by the combustion of fuel like furnace oil and diesel like fuel. Then another type is called the stationary pot type. This crucible is stationary. Okay. Then this is the flame. Then this is stationary. Okay. This is stationary. Then this the ladle, the small this kind of ladle is used to take out the molten metal from the crucible. Okay, from the crucible. So then another type, tilting type. Okay, tilting type is like this. This is the flame. Then there is steel housing, and this is the crucible. So then this is the charged material. Then there's a hole to evolve the fumes also. Then what happens if it is mounted on this kind of stand? After it produces the molten metal, this is the flame. This entire assembly can tilt to take out the molten metal. Take out the molten metal to this kind of ladle for pouring. Okay. Then this crucible is manufactured using the steel alloy, and cast iron also used to manufacture this crucible when melting the aluminium, lead and copper like metals. Cast iron crucible is used. Okay, cast iron crucible. This crucible is very thick. It has a thick thickness for the durability of the crucible. Then this is the three type of crucible type furnaces used to melt the low melting temperature metals like tin, lead, aluminium, copper like metals. The furnace oil flame. The furnace oil flame is used to produce the heat. normally the furnace oil flame is used to produce the heat, and these are the three type of crucible type furnaces. Okay, and these are the four type of furnaces we discussed used to melt the molten metal, to produce the molten metal. The one is the cupola, second one is the electric arc furnace, third one is the induction type furnace, and the fourth type is the crucible type furnaces. Okay, then we are going to discuss some another important calculations regarding this metal melting. The total energy required for metal melting. Okay, another important calculations regarding this producing the molten metal. The total energy required for metal melting. Okay, then let's see how to calculate this energy required to produce the molten metal. Then we are starting with the solid metal. Solid metal in room temperature. Let's take the room temperature as TR. R means the room temperature. Let's take the mass of this solid as M kilograms. Then what happened? This is in room temperature. So then this temperature have to increases to a melting point. Okay, melting temperature. Okay, it still is solid. The mass is M. Then it has to heat it to a melting temperature. For example, if it is aluminium, it has to heat it to a 650 centigrade for the pure. 650 centigrade, that means the melting point. You see, but it is still a solid. Okay, then the heat energy we have to give. Let's take this is H1 heat has to get. We have to give to take this solid metal to a melting point temperature. So then we have to convert this solid metal to a liquid metal at this temperature by giving the latent heat of fusion. Let's take H2. To break the bond molecular structure, we have to give the latent heat of fusion. I think you all know this latent heat of fusion in your O level. Okay, it produces the molten metal at that temperature. The temperature doesn't change. That means the energy, the heat energy given in this situation is totally used to break the bond internal molecular structure, to break this internal molecular structure bonds, and to convert the liquid metal at the melting temperature. So then what happened? We can't take this molten metal to pouring. What happens if we take this molten metal to a pouring to a mold? This immediately solidifies. No, it immediately becomes solid when it just pouring. Okay, it may become solidified solid in the runner system also. So we have to increase the temperature to a pouring temperature. Okay, let's take for the aluminium, this is let's take 650 centigrade. Then here also 650 centigrade. So then we are taken to some elevated temperature for pouring. Okay, some elevated temperature for pouring around 750 centigrade, like that, for example. Okay, let's take this temperature as the pouring temperature TP. The pouring temperature is greater than the melting temperature because we need some elevated temperature for pouring. Otherwise, what happens if we take this temperature, it immediately solidifies. So we can't pour the molten metal. So some elevated temperature is used for this temperature. Then energy given this in this situation, let's take H3. Okay. During this entire process, the heat energy loss, let's take it as H4. Okay, heat energy loss, let's take it as H4. The heat energy loss may due to heat energy loss H4. So then the total energy required for this operation is equal to H1 plus H2 plus H3 plus H4. Okay, H4. Okay. So then what happened? Total heat energy required, let's take it as the capital H. So what is H1? Let's take this solid metal specific heat capacity. Specific heat capacity as the CS, specific heat capacity of the solid, CS. Okay, then H1 we can write. What is H1? M CS, we know the temperature difference, Tm minus T room temperature. Then this is the H1 to take this solid to a melting temperature, plus H2. What is H2? Latent heat of fusion. If you know the specific latent heat of fusion for this material, let's take that is equal to HF. Okay, latent heat of fusion of this material. We can calculate this energy required because the mass is given, mass into HF. Okay, plus then this molten metal, liquid molten metal, have to take it to pouring temperature. The mass is same. We should know what is CS, CL, specific heat capacity of the specific heat of liquid metal. Then to pouring temperature TP TP minus Tm plus H loss. Okay, this is the equation we obtain. So then what happen? H is equal, M we can take it out from the, it's a common term, CS, Tm minus Tr plus HF plus Cl, Tp minus Tm plus H loss. Okay, the final equation we can write. Here the M, the mass of this that means actually the finding the mass, instead of finding the mass we can easily find the volume of the part we are going to cast. That means for example, if you are going to manufacture something, this is the product we are going to cast. Let's take this is the product we are going to cast. Okay, this is the product we are going to cast. That means to cast this, that means to manufacture this product, let's say we are going to melt metal for, to cast this product. So in that situation we are knowing this drawing of this diagram. We know the drawing of this diagram. We can easily calculate the volume. Instead of calculating the mass. Okay, so that this mass we are adding M into, this mass is we are adding rho into V. Okay, rho is the density of the material. We are going to. So then H is equal density of the solid metal, CS, Tm minus Tr plus HF plus Cl, Tp minus Tm plus H loss. Here also bracket, no? Sorry, there should be a bracket. Joules. This is the final equation we can use to estimate the total heat energy required for this to produce certain casting. If you know this calculation, we can estimate total coil required for this certain cupola operation. If you know this calculation H value, we can estimate the total energy consumed for this total electricity required for certain casting operation. Okay, then if you know this energy, we can estimate the cost for part. Okay, that is very important calculation in metal casting. That means the total energy required for metal melting. This calculation is very important. Okay, then I will write these terms also. CS Tm melting temperature, Tr room temperature, Tp pouring temperature. Okay, Tp pouring temperature. Then the CS. What is CS? Specific heat of solid. CL. Specific heat of liquid, solid metal. Heat of liquid metal. Then the HF, latent heat of fusion. Latent heat of fusion. Then if we know these things, we can estimate the heat energy required for certain melting operation. So let's do the example problem from this total heat energy required calculation. Okay, let's take the example. So we are going to discuss some past paper questions from this. Okay, this is the question we are going to discuss. I think you will clear this diagram. This is the question we are going to discuss. Yeah. First read, for a certain cupola operation, 800 kg of cast iron has to melt for casting. The following data are given for this operation. Assuming the complete combustion and neglecting the heat loss, calculate the kilogram of coal required for this operation. Here there's two assumptions saying actually this is a very rough calculation. The neglect the assume the complete combustion. We have to assume the complete combustion. That means total that means by combusting this coal we can produce entire this energy, total energy we can produce. That is the assumption, the complete combustion, and neglect the heat loss. The heat loss you can neglect. This data is not given heat loss for the heat loss calculation. We have to estimate the coal required for this operation. Okay. Then how to do this one? Let's see. Okay. The example solution. What is the cast iron? The mass value. The M is equal 800 kilogram. The mass is 800 kilogram. So the data is given. Just we want to substitute the these values in this equation. No, these values in this equation. Okay. The MH is equal MCS. What is that equation? Tm minus Tr plus MHF plus MCl Tp minus Tm plus heat loss. Heat loss is neglect. You are neglecting the heat loss. Then okay. Then what is H? H is equal. What is M? 800. What is CS? So I'm taking the M out because here we are in the M is given. We can take it from. What is CS? CS is given specific heat capacity of the solid is in Joule per kilogram per Kelvin. 660. So I'm not going to put the units. Then temperature difference in what is the temperature difference? Tm, room temperature is 25, melting point, melting temperature 1200 minus 25 plus HF, latent heat of fusion is given. Latent heat of fusion of the cast iron 247 into 10 to the power of 3 plus Cl, the specific heat of liquid cast iron 950. Then the pouring temperature is 1400 minus 1200 melting temperature. Then we are getting the total heat energy required in joules. Okay, total heat energy required in joules. Let me calculate this one. Calculate this one. This is equal to 800 into 12500. Then H is equal 970 into 10 to the power of 6 joules. Please check this answer. Okay, that means total heat energy required is equal 970 mega joules. This much of energy required for this melting operation, neglecting the heat loss and everything. Okay, so then how to estimate the coal required? How to estimate the coal required? Total heat energy required is 970 megajoules. By combustion of 1 kilogram of coal, the 1 kilogram of coal, that means specific energy of coal is given the 25 megajoule per kilogram. So that means we are assuming the complete combustion and the no heat losses. We can directly divide it by 24. Okay, then we are getting the value. It is equal to, answer is that is equal to 40.417 kilogram of coal is required for this cupola operation. That is a very rough estimation. We didn't consider the heat loss, and also we assume the complete combustion, that we can, in a real situation we can't obtain the complete combustion for the fuel, and also there's also a lot of heat loss. That is a without neglecting heat losses and assuming the complete combustion, this is the required coal amount. Okay, this is another example from this calculation. Then we are going to discuss the type of casting. In industry there's a various type of casting, but we are going to discuss only the common casting types we are going to discuss. So let's see what are these casting types. Type of casting. Okay, in industry the various type of castings are there, but here we are only discussing some common casting processes. Only common casting process we are going to discuss because with the limited time period. So then what are these common casting type we are going to discuss? First one, the most common casting type is the sand casting. Then second, the die casting. Third, permanent mold casting. The fourth, investment casting. Then the fifth, centrifugal casting. The last, we are going to discuss the continuous casting. These are the 6 casting processes we are going to discuss. In here I am giving just introduction to these casting processes. We don't have a time to discuss in detail about these casting processes. I am giving introduction to these casting processes. Okay, first let's look at the sand casting. Okay, first casting method we are going to discuss is the sand casting. Sand casting. So why it is called sand casting? Why it is called sand casting? Why? The sand is used to make the mold. That's why it's called a sand casting. The mold made using the sand mixture. That's why it's called sand casting. Okay, sand is used to make the mold. That's why it's called as sand casting. Okay, actually the sand mixture mean the 90% sand, then the 7% bentonite clay, seven percent 90% sand, 7% bentonite clay, and around the 3% water. Some situation the resin binders are also added to this mixture. Without the resin binders, these are the composition: 90% sand, 7% bentonite clay, and the 3% water. So then sand casting is the most widely using casting method. Okay, sand casting is the widely using casting method in industry. Okay, casting industry. So I will explain. First of all, I am going to explain the component of the sand casting, sand mold. Okay. Components of the sand mold. Component of the sand mold. Okay, let's do the sand mold first. Let's take this is the part we are going to manufacture using this sand casting. Then it also having the internal features also. Let's take. let's take the internal feature as the hollow feature we need. To generate the hollow, the cores are used. I'll explain later. This is called the core. Then okay, then I will draw that one also. Yeah. The runner and also the riser and the sprue. This is the cross-sectional view of the and also the vent hole. I will draw the vent hole also. The vent hole. Then this is sand. Okay, this is sand. You can see the mold is made using the sand mixture. That means by compacting this sand around the pattern, this cavity area is created by compacting the sand mixture. Around the pattern. Okay. Then the molten metal is poured to this through this sprue using this kind of ladle. Okay, let's take this is the molten metal pouring, the liquid molten metal. Then what happens this when it pour to this cavity, then this is sprue fills with the molten metal, then it is passes through this runner system, then this riser get fills, then it is enter to this molten metal enters to this cavity area, Then what happens this when filling the cavity, the trapped air escapes to the vent hole. The certain portion is escaped to the vent hole, and also certain amount is escaped to the sand wall. Okay? Sand wall. So then this is after when it pouring, the molten metal passes through this sprue. First it is passes through this sprue, then runner system. This is called the main runner. Some situation mold may contain the multiple cavities. In the situation, the runner system is divided. This molten metal flow to the different cavities. That means sub runners. This main runner is divided to a sub runner. Then this molten metal taken to each cavity of the mold. Mold does not necessary to having the one cavity. In some cases it having the multiple cavities. In that situation, in a single casting it can produce the multiple product at simultaneously. Okay, especially when manufacturing the small component, the molds are created with the multiple cavities. Okay, at once it can produce multiple items. Okay, multiple items. Okay, here this is the structure, the cross-sectional view of the sand mold. The another thing I forgot to mention. Then this coil is mounted using the chaplets. The coil is mounted using the chaplets like this. It is like this. This is a screw, adjustable screw called chaplets. Okay. Okay, let's see the component of this sand casting. This is called vent hole. This is called screw. This is called runner. Okay. This is called riser. This is called riser. Then this is called the cavity, product cavity. This is the product we are going to manufacture. That means this is the core. The cores are used to generate the internal features. This is called the core, the riser, sand mixture, riser. This is called chaplets. Okay. Then this is the structure of the sand mold. This is the component of the sand mold. Okay. Then the pouring screw, the mortar metal is poured to this pouring screw. Then this pouring screw, the mortar metal enters to the main runner. If there's a multiple cavities, this main mortar metal flow divided to a sub runners to take the mortar metal to a different multiple cavities. So then here it is also only showing the one runner, the main runner. Then this riser is connected to the main runner. This riser, what is the purpose of this riser? Actually, it's not a feature of the component. Finally, actually we are going to manufacture this kind of component. This is the component we are expecting from this casting. This is the hollow feature. This is the part we are expecting from this casting. This kind of part we are expecting to manufacture this in this casting. That means if you take the 3D view, this is the part we are going to manufacture in this casting process. This is the mold, this is the cavity for that one to manufacture this one. So then what is the purpose of this riser? It's like a molten metal reservoir. It reserve molten metal. Why the riser is used? What happened actually the purpose of the riser is to avoid the shrinkage carrier defect in the part. Okay, every metal when it solidifies, most of the metal except few, most of the metal when it become solidification, the total volume shrinkage. Okay, this riser keep molten metal until the part completely solidify. Then it feed molten metal to compensate the lack of volume due to the shrinkage of the part. Okay, lack of volume, shrinkage of the part. So that means this riser design is very important in this metal casting operation. Riser should able to keep molten metal until part completely solidify. Okay, until part completely solidify, because the lack of volume due to shrinkage, it is shrink. That means when it shrink, it away from the mold wall, it shrink away from the mold wall, it gets shrink. Then because of this lack of volume, the vacuum is formed. So then what happens? By keeping the molten metal inside this riser, it feed this lack of volume to compensate this lack of volume molten metal. Okay. Then riser should be able to keep molten metal until the part completely solidify. Why? It should feed molten metal to compensate the lack of volume. That's why it should keep molten metal until part completely solidify. So then riser design is very important in this metal casting operation. Riser have to design the riser's total solidification time should be greater than part total solidification time. Okay, so normally it is designed 1.25 times the part solidification time. In that way, we have to design the dimensions of the riser. We have to design the dimensions of the height and the diameter of the riser. We have to design. Okay, the riser design we are discussing in a later topics. Riser design, how to design riser. In this situation, try to identify the component of the sand mold. These are the components of the sand mold. Then this cavity area, total cavity area, this is a product cavity area and also the runner, and this total cavity area produced by using the pattern. We need the pattern to produce this cavity area. We are placing this pattern, then we are compacting the sand around this pattern, we are creating this cavity. That is how we are creating the cavity, by compacting the sand mixture around the pattern. Then this pattern make using the some machinable material. These patterns are make using the some machinable material, wood, plastic. That means to make this pattern, in this casting operation, machinable, cheap, available, easily available materials are used to make the pattern. They mostly use the wood and also the plastic, and also the is a mass production. Some situation the aluminium and some metals are used to make the pattern also. Okay, then let's see about this pattern first. Okay, I think you all clear with this component of the sand mold, how it operates in casting operation. So let's see about the patterns first. Okay, pattern are used to create the cavity. That means by compacting the sand around the pattern, we are creating the cavity. By compacting the sand around the pattern, we are creating the cavity. Okay, there's a 4 type of the patterns are created using the machinable material like wood, plastic, wax, and also like material, easily available, cheap, machinable material used to make the patterns. There's a 4 type of pattern. There's a different type of patterns, but here we are going to discuss only the 4 type of patterns. Solid patterns, then the second one, split type patterns, the third, mesh plate pattern, the fourth, cope and drag pattern. The various type of patterns are used in industry, but these things I will explain just to get the idea about the pattern. Solid pattern is a solid. Let's take, this is the part we are going to manufacture. Let's take the very simple one, cylinder, this kind of cylinder. The solid pattern also a cylindrical shape object, but the dimensions are different. That means we have to, when manufacture the pattern, we have to give some allowances for the dimensions. Later we are discussing that one also. The solid pattern. Then the split type pattern. It's a split to a different part, normally 2 parts in this case, split. Yeah, I forgot to say something about this previous mold. This is called, actually the top part is called cope, and this is called drag part. Okay, if you take the mold, this is a cope part and the drag part. This top half of the mold is called the cope part, the bottom half of the mold is called the drag part. Okay, keep remember that one, I forget to tell it. Okay, then split type pattern, it is split to a two part. Okay, you can see these two parts is used to make the two halves of the mold, the cope part and the drag cavity area. Then these two cavities are match each other to form the total cavity. So then the mesh plate patterns. So then this is split, actually is a split type object is mounted on the plates. It's kind of plate. In the bottom, the other half is mounted. This is called the mesh plate pattern. Then another one is the most commonly using one is the cope and drag plate patterns. Okay, cope and drag plate patterns contain everything. Contain everything mean to create the mold, not only the product cavity, we need also the runner system and also the risers and also the sprue also. This cope and drag pattern contain everything needed to create this total cavity area. I will draw that one. It is mounted on the plate also, same as in this mesh plate pattern. Okay, this is a plate, wooden plate. Then everything required to manufacture this one. Let's take a cope pattern plate. First I will do the cope pattern plate. This is the cope pattern plate. Okay, then the runner system and also the riser and yeah, okay, everything included. That means to create the runner cavity, riser cavity and the product cavity, everything included in this cope pattern plate. So if we take the drag pattern plate, what happens? The drag pattern plate, to create the bottom cavity area, drag. It's like this. Drag pattern plates, something like this. Drag pattern plate. Runner. Okay. Drag pattern plate. Okay. Then everything included in this pattern plate. We just want to put the flask top of this cope or drag pattern plate. Then by compacting this sand mixture around this on this pattern plate, we can create the total cavity area. So I will explain that one also. So first, when you are using the solid pattern, what happens? To create the runner system, to create the risers, we have to use the separate different type of patterns. The split type patterns also same. The cope and drag patterns are made separately, then mesh each other to create the total cavity area. This one also same. When using this one, we have to create the runner system and risers separately. But when using the cope and drag pattern, everything included in this pattern plate. This is the wooden plate. Then other patterns are attached to this wooden plate. The product cavity, runner system and riser. Everything included. Here also everything included. We just want to put the steel flask top of this pattern plate. Then by compacting the sand mixture, that means by placing the wooden flask, steel flask. Actually it's a steel box like, okay. Steel flask, it's a container, steel container box like container. We can by placing this steel flask top of the one of the pattern plate, by putting the sand, by putting the sand mixture, by compacting the sand, we can create the 1/2 of the cavity, 1/2 of the mold, called the cope part. In the duct part also make separately. Duct part also make separately by placing the steel flask top of this duct part. Then by compacting the sand, then these two parts match each other to form the total cavity. I will explain that one in detail. Okay, let's take how to make the mold, by using this method. Okay, in this previous diagram I forgot to mention that one also. This is a steel flask. Actually, it is a steel box like component called steel flask. So there's a connecting guide pins, tightening screws, and also the guide pins are also there, and also the handling hand also there, to handle the separately. Okay, then I will explain how to make the mold using this inside casting operation. The mold make using the cope and duct pattern plates. Okay, cope and duct pattern plates. Okay, let's take the pattern plate. Then let's take let's take the previous sample, previous product we are going to manufacture, cylindrical casting we are going to produce. Okay, then runner, then this is the okay, this is the pattern plate. Okay, this is cope pattern plate. So then what happened? We are placing steel flask something like this. Okay, I wrote in here. Steel flask something like this. Actually it's a steel box in two sides open. The two sides are open. Okay, having the guide pins to match the this and also the handling handles also. Then it's a steel box and the top and bottom sides are open. Something like this. Okay, then this one is placed top of this steel pattern plate. Okay, then sand mixture, compact by putting this sand, the compact around this on this pattern plate. So before compacting, some situation the graphite spray is applied. For the graphite spray is applied on this pattern plate to avoid the stick. Then sand is compact around this pattern plate. Same as by taking the drag part. Let's take the drag part separately. Same thing we are doing for the drag part. So yeah, this is the runner, this is the productivity area. Then by taking the drag flask, we are by putting on this drag pattern plate, steel flask. We are putting on this pattern plate. We are compacting the sand. So then after compacting this sand, what happened? This is righted. Righted mean this is inverted. Sorry, this is inverted. We are turned other way. Okay. So then finally we are having this kind of cavity area. This kind of cavity. Then it is inverted. This is the steel flask. We are having this kind of cavity. After removing this pattern plate top of this from this top, we are having this kind of cavity. After removing the pattern plate from the after inverting. Okay. Then the runner system. Okay. And also hole for the riser. I forgot to tell something. Before compacting, sprue has to place. Sprue also is separate from the pattern plate, because this kind of conical pattern we have to use to generate the sprue. Okay, so keep remember that one. It is a separate one. We are using this kind of conical shape pattern to create the sprue. That is separated from the pattern plate. Then hole for the sprue outlet when it look from bottom side. Okay. Then this is the cope part. This is the cope part. Then I will draw the drag part. For the drag part, either drag part mold house. Okay. Then what happened? Then after inverting, we can take this part. So then what happened? These two house, we are going to place each other. That means we are going to place this one top of this drag part. Then we can create the complete cavity. Then we can create the by turning, by placing. We are going to top of this drag part. Then there's a for the alignment. There's a guide pins also. We can align this using these guide pins. By placing this top of this cavity, we can create the total cavity. I will just draw the cross-sectional view. If you take the after completing the cavity mold, I will draw the cross-sectional view through this line. Something like this we are having. This is the product riser and the sprue. Okay. Okay. This is called drag part. This is called the cope part. You can see this drag part and the cope part make separately, then these two parts match each other to form the complete cavity. Then you can see this is a sand mixture, compact around this pattern to create the total cavity area. The cope part and drag part make separately, then these two parts are match each other to create the total cavity area. Then what happens when you pour in the mortar metal? The mortar metal poured to this sprue, then the sprue fills with the mortar metal, then it is passes to this runner system, then the riser get fills, then the part fills with the mortar metal. This is how the mold make use in the pattern. This is how mold make use in the pattern. Okay. Then when making the pattern, that is very important to give the allowances, because when in solidification the product gets shrinkage in all the metal except few metals. Except few metals, all the metal gets shrinkage in phase of solidification. What happened? In here we are going to discuss about shrinkage allowances. Shrinkage allowances. What happened? Let's take, this is the dimension we want to manufacture. Okay, let's take the numerical values. The 10 centimeter. Here is 15 centimeter, something like this. So what happens if we make the pattern to exact dimension and casted? What happens when solidification? What happens? It gets shrink. Okay, it gets shrink. That means normally in solidification shrink happen away from the always happen away from the wall of the mold. It gets shrink. So what happens? Finally we are having less than 15 centimeter and less than 10 centimeter product. Okay, we make the pattern to exact dimension what we the product. Finally, after shrinkaging, we are having less than 10 centimeter and less than 15 centimeter because of the shrinkage. So what happens when you are going to manufacture this product? We are giving some allowances for the pattern. Okay, allowances for the pattern. That means this is the pattern. This is the product we own. This is the pattern for that one. We are giving some extra dimension: 15 plus delta 1, 10 plus delta 2, 15 plus delta 1, 10 plus delta 2. Delta 1 means the allowances for the shrinkage. That is depend on the type of material and also the dimension of the part. Okay, actually for certain material, this delta 1 we can write this 15 plus let's take delta into 15. Delta is a constant for that is depend on the certain material. That means for this dimension 10 plus delta into 10. For certain material delta is a constant. Okay, that means we are making the pattern to a oversize. Okay, oversize. For example, let's assume this is make 15.25, 10.2. The finally, if you make the pattern to this much of dimension, finally after shrinkaging we are getting 15 centimeter and 10 centimeter product. That is the thing. That is called shrinkage allowances. Giving shrinkage allowances, making the patterns. That is very important. Okay. Another one. Then after casting, let's take, we want to machine a surface. That means we want to get the smooth surface for this 4 sides. In that situation, we have to give the machining allowances. That is called Okay, machine in allowances. We have to give certain thickness to machine and remove, so that when making the pattern we can't use these dimensions, because after shrinkage it gives 15 and 10 centimeter dimensions, but we want additional dimensions for the machine in allowances. So let's take we want 3 millimeter. That means we have to make this pattern by giving machine allowances 3 millimeter also, 15.25 centimeter plus 3 millimeter plus centimeter plus 3 millimeter. Okay, something like that. This is called the machine allowances. In the previous we discussed shrinkage allowances. That means when making the pattern we have to give shrinkage allowances plus machine allowances. Okay, in that dimension we are making the pattern, then finally we are getting the product. Then we can we have over dimensions for the machine. Then we can obtain by doing the machining we can obtain the required dimensions, final dimensions, and the surface finish we require. Okay. Then we are going to discuss some example problem. This shrinkage allowances and the machine allowances. This is the problem we are going to discuss. Okay. Calculate the pattern dimensions to cast the following object. Top and the bottom and the whole inner have to machine. The important thing is that in this problem the material is cast iron. This product is manufactured in the cast iron. Here these are the allowances given using this kind of chart. Up to 2 feet, these dimensions again 2 feet, up to 2 feet dimensions, shrinkage allowances is given 0.125 inches we have to give. Okay, up to in between the 2 and 4 feet we have to give 0.105 inches shrinkage allowances. Over 4 feet dimensions we have to give 0.083 inches dimensions. Okay, per feet. Okay, per feet. Then machine allowances is given per side is 0.1 inches. Per side is 0.1 inches for the machine allowances. Okay, try to work out this example problem at home. Then we can discuss on next day class. Okay, we can discuss on next day class. So enough for today. Let's continue on next day class. Okay.